Yeah, thanks for having me. Yeah, I want to talk about containerizing pipe and maybe some words where I'm coming from. I'm actually coming from the enterprise. Yesterday we had a kind of a talk where about containers and that in an enterprise environment we kind of like can leverage Docker. And this is an example I prepared to show how we can do this. With regards to Gaikai, we basically have a lot of computers in a data center, so we need to collect their living signals, if you will, and that amounts to a quite astonishing amount of data per day, and we want to provide insights for our operations, but also for BI over a time period, and that amounts to even more data that we need to process, and we are constantly searching for solutions that help us to do that, basically. And this is a prototype which has nothing really to do with what we're doing, but it's kind of a neat way where we could be ending up. Yeah, let me talk about, do a quick introduction. Then how we would build such a distributed pipe and how we can, have a system that is a distributed pipe, works similarly, and is containerized. Then I have an application stack, which is just a proof of concept. Basically, it's what we all know from Twitter. It's the trending topics. The algorithms behind it is a bit different than what Twitter does, to my knowledge. But this is just a showcase to show you how you could do that. And then a short recap. All right, so a long time ago, Unix Pipe has been invented, and that was not even a thought. So we can chain processes together using the output of a process and feeding it into the input of the next process. And this was a quite powerful idea to do computation. And still, every operations person I know is still using that on a daily basis. So this has not changed, I don't know, over like decades, right? This is a guy from Copenhagen. I know that Unix regards to also some people who lived here a long time ago, but he did a nice notation to the Unix philosophy. I mean, we all know that you should do a program and that does one thing and that does it well and not complicated with things you actually don't need. You need to compose or build these applications in that way that they can work together, meaning they are composable with a pipe. And then what Peter Zalos was adding is basically handle text streams, because text or ASCII encoded bytes, if you will, are still a universal interface. We have in the big data, open source thing, we have several formats that we use and we want to leverage compression and everything. You can all do this, but in the end, you process streams of text, and that's still something you don't gain much if you use proprietary binary files. If you stick with that, you gain a lot of flexibility, and I think it's quite important and often forgotten. Okay, now let me start with Apache Kafka. I don't know how many people have heard of it. It's a data hub, and it's a append log. It's a message bus. It's a lot of things, but basically LinkedIn built that in 2008, 2009. They started it and they released it or give it to Apache in 2011. They needed a way to consolidate their enterprise microservice software stack, and they needed to cope with a lot of data, and they figured out that this old notation of the queue is quite powerful because you could push data into that queue, and then from there, you can give it to any other system that you have, meaning microservice for LinkedIn. But as we see here, several databases can be connected to Kafka. Apps can report their metric data or other events they produce, click events, user activity events into Kafka, and then a connected application behind that message bus can then build a view on top of a database or just real time, and that gives you a lot of flexibility. And they built this system. I want to talk a little bit about how this is done because it's a bit different to queues that we are usually using. We have it as a clustered system where we have Kafka brokers. We have a a zookeeper for consensus. This is a zookeeper ensemble. Kafka uses these to store data about like where is the offsets of a topic and yada, yada, yada. Basically, what we need to know is like this broker cluster here. So a topic is just a queue, and it's ordered, strictly ordered, and Kafka makes some guarantees about this, from newer to older messages. One important thing, because it's called named pipes, a topic has a name to address it. Then what Kafka would do for you is basically split this topic apart into partitions. It will create replicas for you, configurable, of course, but it's all defaulted. Then it will distribute all these partitions of one topic onto all the brokers that are available. And now you can imagine having an append log distributed, giving you guarantees about the order being distributed across multiple machines, really leverage some nice features of how you can process data in real time and being fault tolerant about it. Because if any of your connected system fails, you will still have the replica, and you can choose your tolerance about failure, right? You can, like, how many partitions do you want? How many replications do you want? Blah, blah, blah. Then, of course, in every queue, you have a producer API. You need to produce messages to that Kafka topic. You want to consume from that Kafka topic. That's all new. But then there's something new. You can have consumer groups. So you can have processes running on different machines, joining a consumer group, and reading the topic in order. And this order coordination and this offset coordination is done for you by Kafka. So you can have different consumer groups reading from the same topic on different times on their own thing, and you can actually set the offsets back. So as long as you configure Kafka in that way that you hold, like typically installations have a duration of 3 to 7 days, but you can imagine even more time, you can always go back in time and replay the data. And that's also a very nice feature of doing this. Now, last year they introduced the streaming API, and they have two APIs, a low-level one and a high-level one. The low-level one looks very much like Storm. That's actually the system behind Twitter's trending topic, where you can write custom aggregators, custom processes. You build a topology. That's basically how is your messaging flow through the singular processors that you have in your stream processing framework. And then you have a high-level API. The high-level API is very neat. We'll go into some detail to stream and table abstractions. You have simple transformation. That's basically all my values get mapped to this. All my values get flat mapped. You have aggregation, count by key, simple abstractions basically to help you doing ETL work. So a Kafka streaming, like the high-level thing makes a notion of, like, it knows a table and it knows a stream. And if we have a stream and we think of the stream as a changelog, we would have a tuple coming in saying Alice has clicked one time. Then our table looks like this. Then we get Charlie has clicked one time. Our table looks like this. Then we have Alice clicked again. Now we have the table Alice 2 times and Charlie 1 time still. So you can think of a table as just the materialization. It's complicated for my English. Like you build this table out of all the changes and you go back in time. Basically event sourcing, but now you have really like Java-ish APIs to go from a stream to a table and from a table to a stream. And that's also quite neat because now you can have standing queries on those table abstractions in your stream processor. Basically, and they give you joins. Like I can build up this table from like say click on basket thingies, and another one is like cursor position, and then I can join these tables in real time without having a database. Now, so where is this going together? So Kafka featuring Unix, basically the message broker, or the topic, if you will, can be seen as a pipe, and stream processor can be seen as this little program that you have that connects between pipes. So you have a message broker and you have a stream processing job. For this example, I use closure, therefore this logo that has nothing particularly to do. Basically, it's the Kafka Java Streaming API. And then what we're trying to do here is basically build a program that does this. Split text, sketch the frequency of a token, aggregate this token by key, and aggregate the integer value, and then store these values somewhere in a database. So with regard to containers, because this is all done in containers, and we have heard a lot the last 2 days basically about this. For me as a software developer, this is only the thing that now everything looks the same. If I start a container on my laptop, it's the same as if my operation person starts the container on a big installation. And it's the same contract, everything is basically the same. And that makes life easier. So for me, my program is now a container, and if I want to run it, it looks like this. I do the container name and then the args. That's basically the same as saying Java minus jar. It doesn't matter really, it's just another notation, but it makes stuff easy and simple, and we have these arguments. This is all we need to worry about. And everything else is behind the scenes. So what we're doing is to build these pipe, this distributed pipe. We will use console for discovering services in the Docker environment, using Zookeeper, of course, as I explained, to work together with the Kafka broker. And then for sync storage, we use Elasticsearch. But this can be, this is just, it doesn't mean nothing. So for the syntax of console or for a Docker container, we can just pull in an image, connect it to a network, give it some performance hints or basically restrictions, and say you can use up to 4 cores, you can use up to 1 gigabyte of memory. We can then configure the environment of the thing, and we give it ports because this service apparently wants ports open. And we have this container defined, and it lands on our Docker container, Docker daemon, and we are done. Then we add Zookeeper, the same thing. We add Kafka, and then on top of that, we add Elasticsearch, and like, I don't know if you know the notion, some services just start without any additional configuration needed, and some you want to configure. And depending on the Docker file you have, you can have arbitrarily tweaking opportunities. For instance, I can set the heap space for Elasticsearch as an environment variable, but I can also use the command line arguments to configure whatever the bind host or something. So it's still configurable. So this would be my distributed pipe within Docker on my laptop. I have 1 Docker daemon and a few containers to spawn Kafka. Now, a short recap on stream processors. I don't know how familiar people are with that. If we think of the power, like what we can do with a modern stream processor and what it takes us to run it or to operate it, we will have simplicity and power. Historically, already mentioned, Twitter uses Storm and contributed it to Apache, and it was quite complicated actually to operate. It wouldn't integrate with Hadoop or anything like that, but so you needed your whole new infrastructure, whole new provisioning, blah, blah, blah. The operation team need to be trained on how to run this in like a reasonable scale. And the APIs were just like very, very low level. And it was very, very hard to debug it. Now, like I would say, the most modern stream processor would be possibly Flink. You have an execution that is runs on top of Hadoop, and you have multiple APIs, not just doing ETL stuff, but also doing machine learning, graph processing, and everything. It's a full-fledged modern stream processor. Spark is the same, only that Spark has some other notions how they run the stream. It's not actually a stream processor, it's a micro-batch processor. It's details that we can discuss afterwards, but it's different. It's kind of like, yeah, it's different. So Kafka is not that powerful, as I mentioned. The APIs are not that capable like the ones of Flink or Spark, but it's really, really simple. What you just need to do is basically run jar files across your cluster. And that's it. Configure the network, and that's it. You don't need Hadoop. You don't need another scheduler or something. It's just all within Kafka. So Spark and Flink, as mentioned, run on Hadoop, and Kafka streams run on Kafka. And it's, yeah, as I said, just a jar. So for operations, or if you want to save some time or be faster, it may be beneficial to you to not use Hadoop anymore. And it's still 15 years old. We have better distributed file systems. Yeah, you could. Yeah, I think that's the way to go. But and I propose that all the time. But still, Hadoop is of course there. But you don't need it to do a bunch of stuff that you couldn't do before Kafka streams. Now the tool stack is basically these 4 programs. We have like. These are 4 closure programs. You can look up at GitHub. I would just briefly go into detail for the heavy hitter, which is a trending topic, but yeah, and the other one we will see. And yeah, yesterday we had a talk about Fortran, which is a really old language, and then this is Lispy, and that's also really old stuff, but I like it very much. It's leverage, simplicity, and it yeah, it's quite cool, I guess. I like it very much. So the first program would simply take a text line and then would put it into a list of tokens. That's just splitting on white space, nothing too fancy. The heavy hitter now goes and takes this list of tokens and estimates their frequency. So how often do I see a token in the stream? But the heavy hitter estimates. It doesn't count. Like it's not like it sees everything and counts and do +1, +1, +1. It's an estimated thing, and I will explain how it's been done. So for doing that, there's a distributed a probabilistic data structure called count, min, sketch, and it is quite neat because you can choose a number of buckets in your hash table, and you can choose a number of hash functions you want to apply. And so the sample size you want to sample is basically the amount of buckets you have, and the precision you want to have for your estimate is the amount of hash functions you want to apply. And then you would go and hash an item through all hash functions you have, and then for the bucket position, you would just increment the item, and magically, if you retrieve the estimated frequency value, you would just do the same thing, get all the current numbers, and then take the minimum of all that numbers. And for the details of that, yeah, it's a bit too complicated, but it works quite well. So now you have a fixed size of computational space in time and space, yeah. So you can just, basically, if you know your data very well and you know your size and you know your precision level, you have a fixed fixed number of CPU cycles and a fixed size of memory allocation to do frequency counting on an arbitrary set of tokens. And to implement a heavy hitter, you would use the min sketch, and then every window, time window, like you look for a minute or 5 minutes, you would take all the items in that bucket and store it in a hash table sorted by frequency. And then you have your heavy hitter. That's your trending topics in Twitter. Just that these values are estimated, and Twitter, I believe, counts one by one. So yeah, now this is source code. So such a heavy hitter processor would be done doing building a processor, and the get processor is the one where I actually get the processor. Then you would have a state. That's the state where we have like the number that we estimated. And this state will be propagated across the Kafka broker cluster and will be synced across our processes that are running, doing the stream processing. So this processor looks actually, it's very simple. You basically have an init function where I set up my heavy hitter sketch structure, and I schedule this processor for a time window. And that's like any long number, I guess it's a minute here. And then every 1 minute, on the last function, on the punctuate, let me talk about later, that's the init. So then every time we see a tuple, we will sketch the value and add it to our heavy hitter thing. And then on punctuate, and that's been called when the time window is over, we will sync back our local storage across the cluster, and then they will join the values. And then when we are done, we can close. That's the last thing. And same thing here. If you want to have it as a container, you basically build a jar file, write your Docker file, give it a name, let join a network, and then have the command line arguments, and it's configured. So basically, we just need to connect it to a broker. We need to say, where's your input, like where you want to read from. That would be the name of our pipe where we're reading from. And then we have an output name where we have the topic where we're writing to. Now, when we have these estimated values, because it's distributed, we need to, on a final phase, aggregate all these values into one number, because the stream out of that heavy hitter could have the same token with a different number estimated, and then the final step would just aggregate it together. And then when we have this aggregation, we will convert this to a JSON, because our Elasticsearch thing just loves JSON, and we transform it in the last step, make a JSON, and index it to Elasticsearch. So as a repetition, we have the line of text, we have the tokens of the line of text, we have the estimated values of the tokens, we have the aggregated values of one token, and then we have the JSON blob that we store in our final database. And then what you get out of it is basically, for every 1 minute, you have the amount, like a number of counts for a specific token. And the winner here is, I can't read it actually. But you see that this is variating, and that you have for every minute, you have basically the trending topic estimated. On my machine, that looks still the same thing. I have my 4 Docker containers and my distributed pipe for my stream processors. And if I want to go to the data center now, I would just build a Docker swarm and have multiple Docker daemons running on multiple hosts. And then Docker swarm will basically schedule these containers to be run on different hosts. I have control over that, but it also runs out of the box. But yeah, of course, if you have bigger setups, you would do this. And then on your machine, you shouldn't do that, but your operations person would just set the Docker host to the swarm node, and then that's it, basically. Then you deploy the same thing. As I deployed it on my laptop, you deployed this on a data center. There are still challenges, of course. Kafka Streams has only at least one semantic, which means items get delivered more often than once. This persistent storage is hard to debug. You still need capacity planning. Of course, the laptop is something different than a whole data center, so the amount of partitions you need to have would be different. Testing and debugging is hard because of this store. You need to look at each and every machine if something goes wrong in a distributed way, but I guess that's all very familiar stuff for the people here. And then you have this notion of event and processing time. So what are you counting on the time something happened, or on the time something goes through your pipeline? That's a different thing, and that can also be quite tricky to get the numbers right. And then there's Amdahl's law. It's like your gain that you have by parallelizing across multiple machines will come to an end at some point. And you need to figure out for your domain where this actually is. So recap would be use pipes, use simple programs. A pipe can be a message broker. A simple program can be implemented as a stream processing job. Then you put it into Docker to run it everywhere, and you're good. That's it, basically. I'm done. Any questions?